Okay, welcome to this uh, evening of the Computational Challenge. It's very good to see so many of you here. This week it's a little bit different. Andy French is away, and it's an opportunity for us to show you how to actually use Python without rushing through lots of sort of actual physics as well, which certainly keeps you on your toes. So we've got Ben Raddick and Sophie Glencross. Um, who are experienced in using Python and are going to show you some various steps, how to get started and things that you can do, how to plot graphs and so on. So have a bit of paper, take some odd notes about things you can do, not all the details, trying to write down code and so on of how it's done. You can easily look these things up, but seeing this overall picture, how you kind of link things together, that's extremely important and is given by a benefit of experience from these two. So let's make a start, and I think Ben is going to start you off.
Yes,
Okay.
hello everyone. My name is Ben. I'm a PhD student at the University of Oxford, studying physics. And so today we're just going to walk you through how to use some software for writing in Python. So what I've got on my screen right now is a graph that I made just last week, which I'm using as a part of my research. Um, I won't go into the details of what it shows, but I think it's quite a nice graph. And so our aim today is that by the end of this session, you'll be on the way to learning how to make cool graphs like this one. But to start off with, we're gonna strip things back, and I'm gonna show you first just how to open uh, Python. We sent out instructions about how to download Anaconda beforehand. So hopefully you've been able to download that. If you haven't, don't worry. We're going to upload this to YouTube, so you'll be able to watch it back later. And so for now, you can just watch and follow along. So I'm on Windows, so it might be different if you're on Apple, but it will be basically the same. So what you're going to do is you're going to go down to the search bar, and I'm going to search Anaconda like this. And you see it pops up pretty quickly. It's the Anaconda Navigator. So you're going to select Anaconda Navigator, and don't worry if it doesn't respond immediately. It takes about 30 seconds or so um, to load. So if you can all try and start loading that now. Um, Once the Anaconda Navigator is loaded, um, it will look something like this. So what Anaconda is it's a whole bunch of uh, pieces of software that you can use for various things. But we don't have time to go into all of it. For now, the relevant thing is this one over here, which I'm circling with my mouse. So this is called Spider. And Spider is what we can use to write Python code. So once your Anaconda is loaded, I want you all to launch Spider. Okay, so once Spider is launched, you'll get something that looks like this. So I'm going to walk you through what you're looking at, and if there's any text in the left hand side, you can delete it. So on the left hand side, we've got input. So the idea is you input something into the program, and it will output it on the right hand side. So here we put in our text on the left, and on the right hand side we have all sorts of outputs. So we could have graphs. Previously I was showing you that graph in the top right. And in this bottom right, we have text output. So if the output is some text, it will show up here. I think that will be more clear as we go on. So that's the overall layout. And so in the first half of the seminar, I'm going to introduce some of the basic things you can do with Python. And then in the second half, Sophie is going to take over and she's going to show you how to make some graphs. So I'm going to start with the following command. I'm going to say print hello world. So I've typed the command over here, and then I'm going to go up to the run bar. So this green play button, if you press that, then it'll run the program. So let's see what happens if I do that. So I press it, and what we see is over here, if you look closely, we see that something happened, and now the program returns hello world. So the idea is that I told it to print this phrase, hello world, and it returns hello world. Now you have to be precise with what you type. So you have to make sure to include the quotation marks either side of hello world. Otherwise it won't work. So for example, if I make a mistake like this and I didn't quite print the right thing, then I'll get an error message over here. Now error messages, they're okay. Error messages are there to help you. There's nothing wrong with making a mistake whilst coding. That's a part of the process. Most of your time spent coding will be trying to fix a mistake that you've made. We call them bugs. So yeah, so over here it tells me I've got some error. It's okay. You don't need to understand exactly what's going on. But through problem solving, you might realize that actually I needed to have that quotation mark there at the end. And there, I run it, hello world. If you want to not run a command that you've typed, you put a hashtag in front of it. So for example, I might want to make some comments. So I say, this prints hello world. And then that reminds myself what this line above does. And I'm going to comment most of my commands in this session, just so that if you fall behind, you can see what I typed earlier. Right. So we can print other things. I can print it's Thursday, if I can spell Thursday, which I think I can. And we see in the bottom right, we get it's Thursday. So, have a play around with this, print whatever messages you want to. So this is one thing you can do with Python. Okay, so we can print things. What else can we do? Well, we can use something that computers are very good at generally is dealing with numbers. So in the most simple example of that is that we can use Python as a calculator. And if you want more space in the command line over here, you can just press enter a few times and it gives you a bit less clutter. Right. So how do I use it as a calculator? I can do things like this. I say print because I want to see the output. 2 plus 2. So I'm expecting to get 4 in the bottom right. So I do that. And what do we get? We get 4. There we go. Okay, so we can do very simple things, but I can also very easily add 2 really big numbers. I'll say print 1 with loads of zeros plus 27, and Python can do that no issue, and there it is, print it right there. So we can add big numbers. We need to be able to multiply. So to multiply 2 numbers, you might think that you do sort of like 6 times 7, but actually you have to use a star for multiplication. Learning Python is just like learning a language. Like it's like learning French or something, where you just kind of have to learn the rules sometimes. So they use star for multiplication. So if I do 6 times 7 and I press run, then I get 42 in the bottom right, as we expected. Great. So we can multiply. What else can we do? Well, I want to be able to take away for sure. I want to be able to do subtraction. Let me see. If I do 30 minus 27, then I get 3, as expected, down in the bottom right. Okay, let's see. Addition, multiplication, division. We definitely need to be able to do division. So how do I do 20 divided by 10, for example? So to do division, you need to use a slash like this. So 20 slash 10 means 20 divided by 10. So if I run that, I get 2 on this side. Now notice that it returns 2.0, not just 2. So something to be aware of in Python is that there's different data types. So you can have integers, like integer data types, which is just like 2, 3, 5. Then you can also have like the decimal kind of data types. So that's like 4.3, 2.7. And so when you divide, you get a decimal, which is why you get 2.0. So that's just something to be aware about. Um, so, now, let me ask you kind of rhetorically, what do you think we will get if I print 2 divided by 3? So just, yeah. So, in a decimal form, we'd get 0.66666, 6 going on forever. But, computers can't do that. They're not infinite. So they run out of space. So when I run this, I'm actually going to get 0.66666, but it eventually stops. So yeah, so it stops after a certain amount of time. So that's something to be aware about when you're dividing things. Okay, we can divide, multiply, add, subtract. This is all good stuff. So what next? Next, we're going to learn how to exponentiate. So how to use powers. So maybe I want to do 8 squared. So 8 squared, I expect it to be 64. So 8, and the way you do a power is with 2 asterisks like this. So 8 to the power of 2 is 8 star star 2. So if I run that, what do I get? I get 64. So it works. That's good. Just a couple more things before we move on to something else. A very useful operation is to be able to round down. Okay, so I can print int of a number like 4.4. So what int does is it rounds down to the nearest integer. So int of 4.4 will give me 4. So let's double check that. Yep, there we go. Yep. And again, if I'd made a mistake and I hadn't included the right number of brackets, and I run this, then I'll get an error down here. But remember, errors are okay. They're there to help us. So in this case, the syntax error is that bracket was never closed. So it's quite helpful this time. Sometimes error messages can be pretty daunting, but as you practice more and more, you'll learn how to read the error messages. Right. So just as a quick test, what do you think we're going to get if we print int of 2.0? So what are we going to get? So what we get is 2. So we don't get 2.0, we get 2. So that might not seem like it matters, but for Python it does matter because those are different data types. So 2.0 is the decimal type. The technical language is that we say it's a float, but it's a decimal, whereas 2 is an integer. So whilst like in your maths class, it doesn't matter to distinguish between those. When you're doing code, those sorts of things can actually matter. Okay, so right, we can use Python to print messages. We can use Python as a calculator. Um, what else can we do? So an important idea in Python is that of a variable. Um, so I can say A equals 7 and B equals 2, and then I can say print A times B. And so when Python reads this, when Python sees A times B, it says, what's A and what's B? And it goes up earlier and it sees, A is 7, B is 2. So if I run this, I'm expecting to get 14, and I do indeed get 14. Great. Um, but variables are very, very general. It doesn't have to be a number. So like I could have a variable be actually let me hash this so that people can still see it later. I could have instead created a variable called message, and the message is hello world. And then if I say print message, if I make the mistake of not spelling message right, then I get an error. So here's another possible error. It says name error. Name message is not defined. So all that means is that I go back here and I say, I realize I've got too many S's. So I'm going to print message, and then we get hello world back again. Um, I could have also reassigned the variable name. So um, I could have said, x equals 3, and then y equals x, and then print y. And then that's going to print y, which is x, which is 3. I think one important thing to note is that once you've assigned a variable, you can then update that variable as well. So you can say x is 3, and then say x is now 6. And if I now print x, it will go to the latest version. So it will print x is 6, which you see down here. Also, if you can also do things like this, where you say x equals x plus 7. So in this case, this line takes the old version of x, adds 7, and that gives you a new version of x. So we're going to get 10. So this is a little bit different from your math class, because if you saw the equation x equals x plus 7 in your maths class, then you take away x from both sides and you get 0 equals 7, which doesn't make any sense. So this isn't an equality like in maths. This is us assigning a value to a variable. So we're saying the new value of x is the old value of x plus 7. Okay, good. Okay, so we've talked about how to print messages, how to use it as a calculator, and how to assign variable names. So one of the things that makes computers really powerful is that they can do very simple actions very, very quickly. So that makes them they're much better at that than humans. So I'm sure many of you can do your times tables very, very quickly. But I guarantee you that Python can do it faster than you. So right now, let's make a loop that calculates the multiplication table for numbers between 1 and 10. And we're going to do that with what's called a for loop. So I'll just type this out and do so for I in range 10, and then for j in range 10, print I times j. So what I'm doing here is I'm saying I'm creating a variable I, which takes 10 values. Now, annoyingly, it doesn't go from 1 to 10, it goes from 0 to 9. So that's something to bear in mind. Um, and then for each value of I, um, I'm making a value of j, which also goes from 0 to 9. And then I'm printing I times j. So what I'm essentially doing is I'm saying, you know, take every number from 1 to 10, and for each of those numbers, again, take every number from 1 to 10, and then multiply them, and then print all of those. So if I now run this, we're going to get a lot of numbers on the right-hand side. So you see, we got a lot of numbers over here. Um, so these were the numbers where it was 0 times 0, 0 times 1, 0 times 2. And then there was 1 times 1, 1 times 2, 1 times 3. And here we have 2 times 1, 2 times 2, 2 times 3, and so on. And so you see, Python is very quickly able to give you the full multiplication table. And the last entry is 9 times 9, which is 81. But you see, it does it almost instantly, right? Um, in fact, we could make these numbers much, much bigger. So we could do this for all multiplications up to 1,000 times 1,000. And and Python will do it really quickly. Uh, so let's see. So 1,000 times 1,000. If I have a square with 1,000 things on this side and 1,000 things on this side, how big is the square? It's got 1,000,000 entries. So let's see how quickly Python can create 1,000,000 answers. So I run it. There it goes, and it's done. So I think that was about 3 seconds. Um, so I think that's a little demonstration just to show you just how fast Python is. So just think about it. We just printed 1,000,000 things in about 3 seconds, um, which is pretty cool. Yeah. Yeah, this stuff is very powerful. Okay, so we know how to print messages. We know how to use it as a calculator. We know how to assign variables. We've looked at how to create loops. We call these for loops. Yeah, these loops. Um, Next up, just to transition into Sophie's part of the talk, I want to introduce the notion of an array. So for this, you're going to want to import what's called NumPy. So NumPy is just a useful thing. We normally write import NumPy as NP. You don't really need to know what it means. It's just somebody else has written some useful code, and we're going to use that. And what you can do with this is you can create an array. So an array is just a grid of numbers. So I could have just a sort of one-dimensional grid where I have like 3, 7, 2, or I could have like a square grid of numbers, or even a cube of numbers. All of those things are called arrays, and they're very useful. So an example of an array is I could say I'm going to assign the variable a, and I'm going to say np.array. I'm saying numpy dot array, basically. And so I could do 1, 3, minus 0.2. And then I could print a just to see what it looks like. You see 1 point nothing, 3 point nothing, minus 0.2. And I think I'll keep it as just integers, just to keep things nicer. And just real quick, one nice thing about Spider, the reason that we got you all to use Spider rather than something else, is it has this thing over here called a variable explorer. Now, if you go here, you can see all the variables that you've defined, and you can see what some information about them. So, for example, we see that A, which we just defined, is an array of integers of size 3.
Ben,
And in
sorry.
fact, oh,
Sorry. Can you just scroll down a little bit to get the interesting part in the middle of the screen? Yeah, from your code on the left-hand side.
yep,
Thank you.
yep. Is that better? Yeah, I'll presume so.
Yeah, thank you.
Thanks. Yes. Yeah, sorry, if anyone couldn't see that, there's what I just wrote. So if you double click on A, then you can see in a kind of nice graphical format what the array looks like. I could also have created like a cube array. So I'll show you how I do that. I say np.array 1 0 3 4. That's going to have to be this. And if we run that and then we check out what the variable looks like, it's 1034, and it's a nice queue of values. Okay, so that's everything from my half. Hope you've all got something from that, and now I'm going to hand over to Sophie.
Hello. So I'll just share my screen. So this is also Spider. So if you go up to the top left-hand corner up here, you can find the new file button. So I've just done that and have a new file up here. So in order to plot some graphs, we're going to need a couple of libraries. So just going to import those. One of them is going to be NumPy, which we were just using. And the other one is going to be matplotlib. Matplotlib.pyplot.
Sophie, you've frozen.
So
Sophie, you've frozen. You need to repeat again.
Okay, so we've imported these libraries, and we have called this matplotlib.pyplot plt just so that we don't have to type all of this out. And it's one of the popular graphing libraries in Python. So we're going to start by plotting y equals x. So we're going to use the linspace function for that. So which is found in the NumPy library. So when you've typed that out, you get this helpful box that comes up, and it tells you that it returns evenly spaced numbers over a specified interval. So we're going to start on numbers from 0, and we're going to go up to 10. And we're going to use the default number, which is 50. But if you were to change that, you could just put in how many numbers you'd want. So we're going to then have 0 to 10. And that's going to get us an array of numbers that go that count from 0 to 10, with 50 numbers in between. And then we're going to plot this, and that's going to be plt dot. So in this you would put then your x data and then your y data, but because we're going to plot y equals x, we're going to have x. You need to make sure that you're on the right tab here. So you want to be on the plots tab, not the variable explorer. Something else that can be quite helpful is having labels on the axes. So if we type in plt dot, we then need to try and work out what function would give us these labels. So if we type in plt dot x, we can then look at all the functions that will give us something to do with the x-axis. So this is actually even all the functions that begin with the letter x. So if we go through these, we can then read the descriptions that appear here. And then if we go to the x label description, you can see that that's giving the description of what we want to do. So we press the tab button and that will auto complete. And then for now we'll just put that as X and do the same for the y-axis. And then if we run this, you can see that we now have X and Y labels on our axes. Now, there are much more interesting graphs that we can draw as well. So we could try creating a sine graph. So we can then say let y equals mp dot sine x. And then instead of plotting x against x, we then want to plot x against y. So what this does is it for every value of x that we have, so remember we have 50 different values that appear in the array of x values, it's going to calculate the sine of that. So there's going to be 50 values in y, and each one of those is going to be the sine of the corresponding value in x. So should we run this and then see what output we get? And now you can see you get this curve here, which is a sine curve. If you might have seen this before, this kind of pattern before. Now, one thing you have to bear in mind is that, as you can see here, the period of this sine wave is just over 6. And it turns out that this value is 2 pi. So you have to bear in mind that the sine function works in radians, which you might or might not have seen at school before. If you haven't, I'm sure you'll see it soon. But just when using the trigonometric functions in Python, you have to be very careful about what you're doing. There are, if you don't know how to convert between them, there are functions available in Python that will do the conversion for you. So now it's also often interesting to be able to plot multiple curves on the same graph. So we can also do a cos graph. So we can instead of I'll just move this down a bit. So we'll do this. This all does the sine graph, and then we'll do the cos graph here. So instead, we'll add plt dot plot, and then we're going to want to keep the same x values, but we'll change the y values so that they're cos values, the cos of the x values. So instead of just creating a variable y that we can make the sine, we can put the cos directly into the plot function. So we can put cos x here because this is the value that we're passing in as y. Now we can run this, and now you can see we've got an extra curve that has appeared on our graph. Now we know that the orange curve is the cos one and the blue one is the sine one, because the cos one appeared after we'd added the orange one appeared after we'd added the cos function. But if you were just to give this graph to someone, they might not know. So it's very helpful to be able to label them. So to do that, we use the label keyword, and we say type label equals. And then here we add a string, and I'm going to call this one y equals sine x. And then the cos one, we're going to call y equals cos x. And now we need to tell the program that we want to display these labels, which we do using the plt.legend command. And if we run this again, you get this little legend that appears in the bottom left corner with y equals sine x and y equals cos x. Now, another thing that can be interesting to add to a graph is if, say, we wanted to identify a single point, say, for example, this intersection point here. Now, the plot command uses, it takes the consecutive values in your array, so the consecutive values of pairs of data, and it draws a line between them. Now, if we were only to pass in one value, we wouldn't get a line as it can't join. It doesn't have anything to join it to. It is possible to change that using the formatting available in Python, but The way I'm going to show is using a scatter plot. So we're going to use plt.scatter. And then I happen to know that the value of this point, it happens at x equals pi over 4 and y is square root of 2 over 2. And then we can also add a label to this. And then if we run this again, you can see that this point has appeared here, and we've also got this point in the legend as well. Now, are there any questions about what we've done so far?
Yeah, we're getting through them, I think. No worries.
Yeah. So now I'm going to try showing a physics example. So we're going to try plotting some radioactive decay. So I'm just going to swap to this PowerPoint slide for a second. So you might have seen these equations before. So this tells us that the change in the number of nuclei in a time delta t is equal to the is proportional to the number of nuclei that we have and how long the time we've been watching the time step is. So that's the number of nuclei to decay in that time step. And this equation holds for delta t is fairly small. Lambda here is the decay constant, which depends on the nucleus. It is related to the time constant, as you can see over here, to the half-life. But we don't need to worry about that for today. Just if you might have seen that, you might be more familiar with the half-life. The decay constant is related to that. And the minus sign just means that the number of nuclei that we have is decreasing. So this is the equation that we're going to have to program. So we through each of our steps, we're going to have to change the new number of nuclei to be the old number of nuclei, and then minus this change in the number of nuclei that we have. Okay, so we'll go back to Spider. And I'm going to create a new file. So we're going to import NumPy and matplotlib. And then we're going to start by declaring some of the variables. So the decay constant we know we're going to need. And for this, I'm just going to choose a value of 3. If you were to look up an actual isotope, you would find a value that would be specific to that isotope. But I'm just going to pick 3 for this example. And then we're going to choose a time step, which I'm going to pick is 0.1, and then a maximum time of 10. And we're also going to need to know how many nuclei we have at the start. So I'm going to call that n0. So to mean n, the value of n at the time t equals 0, and we'll have that as 1000. And then we're going to need to calculate the number of nuclei at each time. And then we're going to also need to plot the number plot the nuclei against the time. Now, when you're starting to think about writing a program, it can be quite helpful to go through and write out some comments of what steps you're going to take, just so that you can plan through and you know what your final target is. So from having done this, we know that we're going to need two arrays, one of which contains the number of nuclei and one of which contains the times, because you know in the previous examples we were having to pass in X and Y as the two things that we're going to have on our X and our Y axis. So to have that, we're going to need to have arrays of which contain both nuclei and time, and they're going to need to be of a length, the number of steps that we're going to have to take. So we're going to calculate the number of steps. And we're going to declare that to be max time divided by the time step. And then we will make sure that we have our arrays ready. So to start with, they're just going to be arrays that are full of zeros, but we'll change that as we loop through. We'll assign values into that later on, which you'll see soon. And we need an array of nuclei to be the same length. Okay, and then we need to calculate the number of nuclei at each time. So we start with having the number of nuclei will start off being n0 because that's what the value is at the start. And then we have to loop through our different times. So we're going to do number of steps. So this will give us the right number of iteration times we go through the loop. And at each time, we will have completed I steps beforehand, which means that the current time will be I times the step time. So we will assign that to times. Time step. And then nuclei I we will set to be equal to n. And after this, we have to get ready for the next step by updating the value of n using the formula we saw earlier. So n is equal to n minus n times decay constant multiplied by the time step. So as Ben was saying earlier, this is another one of the equations that you can't treat as an algebraic thing, because if you try to solve it in terms of maths, you would get that the change is 0, but that's not what we want to do. We do just want to see this as this right-hand side is calculated and is a value, and then we're going to put that value into the variable n. Okay, so this should give us what we're looking for in our arrays that are times and nuclei. So to check that, we're just going to print times and then print nuclei. And see whether this, just to check that we're doing the right thing, because it's much easier to debug this as we go along and check that we haven't made any mistakes now, rather than finding out whether we've made mistakes while we're trying to plot a graph and not knowing whether it was here we made the mistakes or during the graph plotting. So if we run this, you can see that we do in fact get an error, which is actually one of the kinds of errors that Ben was talking about earlier. See here we have 100.0, which means that we have a float instead of an integer, whereas we needed to have an integer when we were in this line here. So the way we can fix this is by putting the int function around
Sophie, you're frozen again. Yeah. Sophie,
Yeah, I'm back. Sorry,
you're back up.
the internet
I
didn't
think you
cut
really
there.
need to repeat that.
Okay, yes. Do you know how long ago it was that I cut out?
You were just fixing that error. So you were
Okay,
putting
yeah.
the integer function
Yes.
around the number of
Yes.
steps.
So, as I was saying, you can't have half a step in your in time. So the number of steps does have to be an integer because then we can have an integer number of things in our array. And then if we run that again, you can see that now we do have the value, the output that we're expecting. So our
I guess Sophie will be back in a moment or two.
sorry, the internet's gone again, but I should be back now, hopefully. Okay, I will start sharing.
We'd just seen the table of results.
Okay, yeah. So I'll just these look as expected. So I'm just going to get rid of the print statements because that's what they've done what we.
Well, I'm sure Sophie will be reconnected in a moment.
Maybe whilst Sophie is getting reconnected, um, I can just say a couple of words about how you can go and learn more yourself. Um, so in general, there's lots of really good um, websites available online. Um, I'm sure we'll be able to put some in the chat. Um, yeah, you can learn loads of great coding stuff from YouTube. In terms of using AI, a lot of people will be tempted to use AI when they're first starting. And whilst AI can be very helpful, I think it's just worth saying that when you're learning this stuff for the first time, try not to rely on AI too much, because then you won't know, what you're doing. Like you need to know, you need to understand what you're doing so you can judge whether what AI gives you um, is actually sensible and correct. So yeah, I just thought that was something worth saying. Okay, I think Sophie's back.
Hopefully, I hope that.
Sophie's accommodation internet is playing up, I think.
Okay. Okay. Well.
Okay, well, Sophie is going to plot a graph when she does get back. So what are the other sorts of things one should be looking at with Python?
Yes. So,
what would be the next
with
steps? I mean, we've seen cos and sine.
Yeah.
So presumably there's a whole raft of functions and various types of graphs you can plot because you can do those 3D kind of surfaces.
Yeah. Yeah, exactly. So if you go on the matplotlib website, there's an official website for matplotlib. They have a whole list of things that you can make, and they have a beautiful list of graphs. And what's also great is that they have example code that you can literally just copy and paste, and put into your own software, to then create the graphs yourself. So I'd recommend you to do that if you want to see more of this. And I also recommend if you do that, you can then play around with the code yourself. Change the color schemes and change the thing that it's plotting. In terms of things that you can do with Python as well, like not only can you plot functions like cos and sine, but you can also plot data, which is really important. So, you collect some data from an experiment, and then you can put that into an array, and then you plot the data, and then you can also plot a function, and you can see how well the data matches the function. So that's something I'm sure you guys have done in school, where you draw a line of best fit by hand if it's like a straight line, and you try and get the line of best fit to go through as many points as possible. But it can be quite hard to do that when it's like a curvy line. But Python's got all sorts of things built in for comparing data to functions. It should also be said that you can do so much more than just make graphs in Python. You can create video games. So that's something I recommend. There's the modules that we've used today are called NumPy and Matplotlib, but there's another module called Pygame, and Pygame has got all sorts of inbuilt abilities for making 2D video games. So and also for making animations. So if any of you have watched Free Blue One Brown on YouTube, he's a maths YouTuber. He makes all of his animations in Python, and he has a lot of beautiful animations. So yeah, he's called Free Blue One Brown. For anyone that hasn't heard of him. Yeah. Do you have any further sort of things I could talk about, Robin?
Well, I'm not sure that Sophie's going to make it back now. By the look of it, she obviously got stuck.
Yeah.
So, um, the sources of data. I mean, what you've done tonight is produce data. You've manufactured it within Python, but can
Yeah.
you read data from other places and then use Python to plot it and analyze it in various ways?
Yes. Yes. I could run through.
Well, not actually showing us off the cuff, because that's
Yeah.
always a bit awkward. Because
Yeah.
but what sort of sources are there for data that people might be interested in for trying it out? Yeah, I mean, I think you can read data from Excel,
Yeah.
um, which
Yes. I mean, because you can get Python to uh, interface with other software like Excel. Um, it's a bit more complicated, but people can definitely learn how to do that. I mean, also like if you've done an experiment and the amount of data isn't too big, then you can just create an array in Python and manually put the numbers in there. But you can also automate that whole process.
yeah, great.
Uh,
Well, Sophie's back. Should we keep our fingers crossed?
I'm not sure. I think I'm not there's two Wi-Fi networks here, and one of them's good and one of them's slightly dodgy, and I haven't been able to get on the good one. So we can give it another go, but
Let's see if we can plot the graph. Yes.
okay.
Yeah.
I'm not confident about this, but okay. So if we put time in seconds on the x-axis and okay, and then we can run this, and then hopefully we left off the plt.show off the end, which is why we didn't get any outputs. But here we go. Here you go.
Okay, I think we've lost Sophie, but just in time to get the graph.
Yes.
Uh,
It is, I think it is an exponential. It's just dropping quite rapidly until it's very close to zero. Then it sort of gets closer and closer to zero, but most of it is just very close to zero. So we can't it doesn't look so much like an exponential when plotted like this, but I think it is.
yeah, so if you've been able to follow the code along, and also we'll upload all the code afterwards, so you can copy and paste it yourself. But if you play around with the parameters, you might be able to make the exponential a bit slower, and then it'll look more like an exponential.
Yes, we're plotting the thing until the radioactive source is completely dead and staying dead for a long time. So, so we get that flat line part, which makes it not so a look-alike an exponential.
Yeah.
Yes, I think, well, I think Sophie's having trouble, but I think we've got that graph. So, Sophie, are you happy with that graph? We finally got to that.
Yes, I think that's as good as it's going to get. The Wi-Fi is really not doing well. Sorry about that.
No, not at all. At all. No, we've got there. So thank you very much for doing this. I hope for all the participants, it's been a good experience and you've seen how you can do some things. Some of you, of course, are very experienced programmers, but that's not everybody's position. So you can learn quite rapidly to do particular things. You're not there to sort of, create an AI monster in a weekend. You're there to learn all about coding starting from the ground upwards, and that is extremely important at university, where you use it and you want to be familiar with it and you want to be comfortable with it, just to do sort of really useful things. And that's very much what it's about, useful things. Okay, well, that's super, Sophie and Ben. Thank you very much indeed for introducing that and showing people how to download it and how just to sort of get started doing stuff. And now they can take it on and test these things out. This video will be uploaded fairly soon. I'm not sure it needs too much editing. I don't think we'll edit anything out. And it'll go up on the BPhO sort of YouTube site. So that's super. So thank you very much. And well, there we are, 9 o'clock. So good evening to you all.